Alright everyone, this is a tutorial for your guided notes on how you can do the hanging stoplight problem. And we'll do it together so you've got it nice and written down, and you can use the guided sheet that we have on our Schoology page for this. So the problem states that a stoplight is hanging by two cables, right? And so with our free body diagram representation, we could label those either F1 and F2, or I like to use the letter T for tension, so T1 and T2. One cord's pulling up to the left, the other cord's pulling up and to the right, and the weight of the stoplight is pulling straight downward. They tell us that the weight of the stoplight is 21 newtons. All they give us are the angles. So we can see there's two unknowns in the problem. Okay, so the FBD right here on the left, this is the correct like free body diagram representation. I just estimated an angle of 30 and 60 here. It doesn't have to be exact, just to get us the idea. And again, what we want to help us visualize are what are our vector components. We could add these together with a graphical method, but we really want to use a component or trig method to help us get a more exact solution. So in this case, if we take a look, I'm breaking, let's say, this red vector down into its vector components. Remember, we choose generally positive in the x direction to the right, negative in the x direction to the left, positive in the y direction upward, and negative in the y direction downward. So our vectors have to have both magnitude and sign. So each of these components, right, create part of the vector component triangle. So I like to write them right on a different diagram. Like I know that if this is T1, okay, right here, this is the opposite side. So this component in the vertical direction would be T1 sine theta. And in this case, right, the magnitude of this component, horizontal component of this force, would be T1 cosine theta 1. And because it's pointing in the backwards direction, right, I give it a negative sign to indicate its direction. And we do the same thing, right, with T2. Over here, the T2 vector we break down in both of the horizontal and vertical components using the sine and cosine appropriately to fraction out that amount of force in each direction. And the weight is only in the negative y direction. It's only pointing straight down. It doesn't have a component horizontally at all. So once we have this down, we can now realize that if the object is in a state of equilibrium, all of these vertical forces have to add up to 0, right? The red vertical, the blue vertical, and the green vertical should add up to 0 in that direction. And these sideways forces are doing a tug-of-war, and they're helping balance the object centrally. It's not moving to the right or to the left, so we are in equilibrium that way as well. So these forces must add up to 0. So what that allows us to do is write a system of equations. Now, what I like to do is I do a T-chart first. Okay, it's just like a nice graphic organizer. It makes me make sure that I've labeled each x and y component. I've checked for each of their negative or positive signs, which way they're pointing. Okay, or if there isn't a component or is a component only in one direction. And the goal is, this is like an accounting table, right, of debits and credits. And this column should add up to 0, and this column should add up to 0. So this allows us to write these equations, which are right over here. So I'm just taking the x column and writing this equation, and I'm taking the y column and I'm writing this equation. So we can see symbolically, right, again, this is the right way to do things. We've got step 1 is our FBD, step 2 T-chart, step 3, right, write our system of equations. Notice I haven't put any numbers in yet. It's a little longer process, but it will stop you from making mistakes and being very frustrated by these kinds of problems. So the more methodical you are, the better off things will go for you in the long run. This is a longer type of a problem that I'm demonstrating for you, kind of like the longest one we'd end up doing. So I'm kind of showing you the whole thing, kind of the right way to do things here. Once we've got the symbols all written out and our two equations set up, notice we have two unknowns. So we've got two equations and two unknowns, so we can expect that we may have to use that. Things become a little clearer when we put the numbers into the equations that we do know. All right, when we substitute in our thetas and substitute in the 21 newtons for our weight, right, our force of gravity, we can definitely see that we're still left with two equations and two unknowns, and you can't just use one of them in this case to solve the problem. So we know what our method is, right, in approaching problems like that. We know we're going to have to solve for one and substitute the expression into the other, and the danger here is simply making a mistake in algebra, because the physics is pretty much done. We've done our free body diagram. We've written those components in equation form based on first law, in this case, equilibrium, right? That we have balanced forces, so the motion of the object's not changing. And we just have to be very careful now. So you could either solve for T1 first, or you could solve for T2 first. I'm just going to choose to write the x equation and begin to solve for T2. So adding T1 cosine 30 to each side, right? And then dividing through by cosine 60 leaves me with a numerical expression, which is T2 equals 1.73 T1. Now we can use that in the y equation, okay? So right in here, where T2 is, right in the top of T2 sine 60, I'll substitute this expression in for my T2 right here, 1.73 T1. All right? So again, just being very careful and laying things out in a way that reduces my chance of making an algebra mistake. So when I multiply the 1.73 by sine 60, I get the 1.498. I'm just going to leave it with this many decimals right now. Sine 30 is 0.5, and I'm substituting in my 21 for my weight. So now you can see all we have to solve for is T1. Okay? So in the, I add these together, and I'm just keeping lots of decimals for now. So I get the 1.998 T1 equals 21, and when I divide through, that's 10.51 newtons, or to 3 digits, 10.5 newtons. Now I can come back up, right, to my expression for T2, put that value in for the T1, and I'll know what the tension in that second string is. So going back, substituting in the 10.51, I get the 1.73 times the 10.51, and resulting finally in 18.2 newtons in the T2 string. So I can see the tension in that second string, right, is greater than the tension in the first string. They're at unequal angles, so we'd expect that. And we know the weight is 21 newtons, right? So we have all three forces now identified. So we'll be using this method throughout the chapter. So it'll be the same method applied to just about every problem we do, except we won't always have two unknowns. There'll be shorter problems than this. So this is one that just kind of encapsulates the whole method and the whole idea of how you should approach these.